few things to notice here. At this point, we have manifest little m goes to big M symmetry, which makes sense because of the original integral is symmetric as we send little m to big M, okay? So that shouldn't surprise us. Another thing that's you could already guess kind of structurally is going to happen here is that because that original integral is IR finite, then as we take little m to 0, that tells us that we should be able to take little m to 0 without encountering any IR divergences. And so all of the little m dependence is going to come as m log m, okay? Now, in the symmetric form, there's no difference between little and big, but of course we're going to expand in a moment, and that'll be the point at which there's a distinction, okay? So in more general EFTs, when you're in a, say, heavy quark effective theory where these types of heavy light integrals show up all the time, you don't necessarily get the extra factor of m in front. You just get these logs by themselves. But again, this is sort of the simplest toy model where we get this kind of structure, okay? So now I can expand in power counting. We get I to rho squared or 16 pi squared, 1 over epsilon plus log mu squared over m squared plus squared over capital M squared log m squared over capital M squared plus order lambda to the 4th. Okay. There's some, I don't know, I think I'm not going to take the time to write some intermediate algebraic steps. It's just manipulating logs and combining fractions and stuff, okay? But you may want to check, I don't know, it's good to check this offline. But notice here we get a log with, that potentially, you know, could spoil perturbation theory. We should be thinking about this mu. We're computing in the full theory, so we should think about the mu way up here, okay? So there's something non-trivial happening here we're gonna have to account for. And then we have this logarithm, which is a function of the ratio of the heavy and the light masses, okay, with no mu dependence. So if we, in principle, if we want to resum this log, then we need to something non-trivial to happen, right? Because we can't use RGE here. There's no mu dependence, okay? So that's the main point of this example is really understanding this logarithm. Now, the downside of this example, so the benefit is that I didn't have to introduce you to any additional EFT technology, write down any new EFT. I just could pick a different interaction in the full theory. But I want to highlight the downside of this example is that the log I'm really interested in is power suppressed, okay? It's proportional to lambda. And so this is actually always small, right? Because lambda log lambda is always going to be small. And so you technically don't need to use these methods here because there's no real problem. Nonetheless, we can, you know, still see the separation of scales. So that's what I'm going to show you. Yeah. Yeah. So okay. So maybe I can write, and that since you asked, I'll write the. Yeah, exactly. I mean, so you have to Taylor expand this, and when you combine, I'm happy to write it. Is that okay? Or okay. Yeah, exactly. So, yeah, but I think the critical thing is going from here to here. You use the power counting, right? You expand. Okay, so so now let's. We of course need to deal with the S-channel diagram. And for the S-channel diagram, for the T and the U-channel diagram, there's no momentum flowing through the propagators, right? I mean, I really should have turned that on its side. And then you don't have to worry about, you can just compute the loop. For the S-channel diagram, unfortunately, it's just a little bit more tedious. So let me just write the integral down, and then I'll write the answer. So now this heavy light log is rho squared mu to the 2 epsilon integral dl 1 over L plus P1 plus P2 squared minus M squared times L squared minus capital M squared, okay? And so, you know, here we just have to keep track of the fact that momentum flows through the loop using the kinematics, I guess, there up at the top, okay? And integrating, doing the power expansion, you can derive I rho squared over 16 pi squared, 1 over epsilon log mu squared over capital M squared. That makes more sense, actually. I think this is a typo in my notes. I think this should be capital M squared. Yeah, it's capital M squared everywhere else. And that makes more sense. Sorry about that. So, good. So then, plus 1 plus M squared over capital M squared log M squared over capital M squared plus 2 plus order lambda to the 4th. Okay, so it's just a little bit more, there's these few other terms that appear just due to that different momentum structure, okay? Good. So one of the, just want to tell a quick story about my own journey with this toy model. So when I was originally designing this example, you know, it's sort of obvious if you're looking for a heavy light integral, this is obviously the simplest thing you can do. And so, so I wrote the toy model down just to, you know, give me this kind of interaction. Did this calculation, did the EFT calculation, and I couldn't get the scales to separate. And so was also, it was under a deadline. I was headed to lecture about this stuff a week later, and this was going to be my primary example. This is kind of the punchline, and I just couldn't get it to work, okay? And so I can't tell you, you know, I bugged everyone around me, helped me think about the factors of 2, because of course there's symmetry factors and so on you have to be careful about. And I was honestly ready to give up. I wasn't actually sure what I was going to do. And so I said, okay, fine. You know, EFT is smarter than I am. It has to work. There's something I'm missing. So I said, let me just get a blank piece of paper, start from scratch, write down the Lagrangian, write down the diagrams. And I realized it's sort of this 11th hour, you know, eureka moment that I was missing a diagram. So there's a tricky diagram that you need to include, and there are various ways of thinking about it. I'll draw it for you in just a second, in order to get this to work, okay? And so the point is that normally when we're doing renormalization theory, right, we just focus on the one particle irreducible diagrams, okay? So for me, it was not something I would have naturally drawn, which is why I was missing it. But when you're doing EFT, when you're doing the matching, you want to focus on one particle irreducible diagrams, but the difference is that you want the one light particle irreducible diagrams. You still can have contributions in the matching where you have internal heavy lines. So in particular, there's a set of diagrams like this, which you have to include, okay? And when you do this, then the matching works, okay? So, and again, you know, for me, this was not a natural thing I would have necessarily drawn because it's not one particle irreducible, right? It's got this propagator in it. But the point is that because we're working in EFT, we shrink this to a point. This is going to contribute on the EFT side as a local operator, okay? And you can think about it also as, you know, contributing to mass mixing. Another way to incorporate this would be to compute the matching, this as kind of a matching correction to the mass, okay? For me, it was more natural to think about it just in terms of this diagram contributing at this order to this process. So we can include this rho squared. Now the symmetry factors matter, so you get a half, right? This is a real scalar bubble, so you get a half symmetry factor there, and this 4 comes from the permutations of the external labels. And then there's this propagator. At threshold, that's a 1 over m squared minus capital M squared. And then the loop, which gives you mu to the 2 epsilon integral dl 1 over L squared minus M squared. And this is straightforward to evaluate. You get minus I rho squared over 8 pi squared, little m squared over big M squared, 1 over epsilon minus log M squared over mu squared plus 1. Okay? So I'll emphasize this again later, but the reason that I knew there was something wrong when I didn't include this is because when I did the matching without this contribution, I was left with log little m dependence in the matching correction, okay? And one of the big messages today is a kind of a technical point, but it's really critical, is that your matching coefficients have to be analytic in the light mass or the parameters of the light theory. In other words, you have to be able to take little m to 0 without changing the matching except by power corrections, right? A non-analytic term like this, a log of little m, if I took little m to 0, my matching correction would blow up, okay? And so if you're going to actually separate scales, then you have to be, your matching should be insensitive to the details of the IR. It shouldn't care if you have small splittings among the masses of the particles and so on, okay? And the way that manifests mathematically is that you should be able to take the little m parameters to 0 at the end of a matching calculation. So you see, when you include this contribution, which follows the rules, it's still one light particle irreducible, it just has a heavy propagator, then there's extra factors of log little m here, and those are the ones that are going to cancel in the matching, okay? So you'll see how that works. So now, where do we land? We can put all of this together to get the amplitude. So we have phi phi goes to phi phi, renormalized. And this is computed at threshold. We have I rho squared over 16 pi squared times 3 log mu squared over big M squared plus little m squared over big M squared, 3 log m squared over big M squared plus 2. Okay, so this, I said this a little bit wrong when I had the typo, but this is just the standard log that we're going to resum by running the rho parameter. Okay, so that uses the techniques we talked about yesterday, right? Just doing standard RG there. This is the potentially large log that we want to understand how to separate scales and resum, okay? Again, in quotes, because of this caveat that it's also power suppressed, okay? So, so we will see that we separate scales there, and in principle we could resum it, it's just that it's never technically large. The log is large, but the whole term is never large, okay? Okay. Any questions about this so far? Notice, right, I renormalized, so I dropped my 1 over epsilons, right? I'm working MS bar. And I wasn't careful, let me just remind you, mu, so for example, in that expression, mu in the top line is just mu in the second line is mu tilde, right? The MS bar scale. So I drop log 4 pi and Euler gammas, okay? Good? Okay, so let's introduce the EFT and separate scales. So we have so we're going to match at tree level. We have C4 equals 0, right? Because in my UV model, I didn't include that coupling, the self-coupling, again for simplicity, right? I'm doing this toy model with the minimal ingredients to make a point. But C6 does get a contribution at tree level, okay? So for C6, I have to include the following diagram, right, at tree level. So here, the overall symmetry factors, you have to be careful about the number of permutations here, okay? So again, this is where it gets to be a bit tedious, but I'll just tell you the answer, leave it for you to do the counting. You get a 10, a factor of 10 when you actually compute the basically, 6 choose 3, and then you divide by 2 because there's 2 sides, and that gives you 10 rho squared, and then minus 1 over capital M squared plus order lambda, okay? And we equate that when we do the matching. So this is the full theory calculation, right? In the EFT, we just have the 6-point vertex. And so we get minus I C6 over M squared in the EFT. And where I've chosen to normalize C6 this way, okay, it's just for convenience. And so equating these gives me tree level condition C6 is minus 10 rho squared. Okay, so I'm just doing diagrammatic matching. And the reason I need this contribution is because in order to reproduce this power suppressed term here, the subleading term, right, I'm going to need the power suppressed contribution at one loop to the 4-point function, and I'm going to get that by closing the loop here, okay? So, So I have this diagram, okay? And this loop gets a symmetry factor of 1/2, right? Like it did up there. And so I have 1/2 C6 over m squared, and then mu to the 2 epsilon integral dl 1 over L squared minus M squared. And that evaluates to I over 32 pi squared C6 over M squared, little m squared times 1 over epsilon plus log mu squared over M squared plus 1 plus order epsilon. Okay, so I recognize the counter term. So well, I'll write it this way. You can tell me if it doesn't make sense. So I have this Z4 that I use to renormalize the 4-point vertex in the EFT. Okay, so I'm isolating the counter term, and this includes minus I 1 over C4 C6 over 32 pi squared little m squared over big M squared 1 over epsilon. So I recognize the anomalous dimension gamma 4 6 is 1 over 16 pi squared little m squared over big M squared. Okay, this is an artifact of the way I chose to define my z's. Okay, remember from 2 days ago maybe, I chose to write things, when I wrote the relation between the bare couplings and the renormalized couplings, I told you I made a choice there, whether or not I included the factor of the coupling in z, okay? And that just leads to this funny looking 1 over C4, but that's not some non-perturbative effect or anything. That's really just coming from the choice of definition, okay? So don't let that confuse you. Okay, so I can use this counter term, subtracts this 1 over epsilon piece, and it also gives me a contribution to the RG, right, which is one of these operator mixing terms. And you can see, you know, another nice thing about this example is that it's very explicit at one loop, right? You get this operator mixing effect. The C6 operator feeds into C4 through one loop diagram, okay? So now let me use this to compute the difference to find the matching correction to C4, okay? So minus I C4 match or one loop. Okay, so you can, if you like, right, the tree level contribution to C4 was 0. Now we're computing the one loop contribution through taking the difference of these two loop calculations. So this we're going to get from taking the full result minus the EFT result. Okay, we get I rho squared over 16 pi squared, 3 log mu squared over m squared plus 1 plus m squared over m squared, 3 log squared over m squared is 2 log m squared over mu squared minus I 5 rho over okay, and this gives us minus I 1 over 10 C6 over 16 pi squared 3 log mu squared over m squared plus 1 plus m squared over big M squared, 3 log mu squared over big M squared plus 5. Okay, so assuming I didn't make any typos, which is I'm not guaranteeing, the right answer is definitely in the TOSI notes. But the point here is that at these intermediate steps, I had these logs of little m, but now my one loop correction to C4 is manifestly independent of log little m, right? So I interpret this mu that appears here like we did yesterday. This is mu sub match, right? I'm computing this at the matching scale. And now I can take mu sub match of order capital M, and I can make these logs small, right? And I get some just simple loop correction at the matching scale, okay? And I can take little m to 0. Had I picked a different kinematic point, I would have had different. Remember, yesterday I was trying to emphasize that little m you should think of as keeping track of whatever the kinematic point was, right? I took threshold, so there were no momentum factors. It was all set by little m. But had I changed my matching, my choice of kinematic point to do the matching, I would have changed all of that dependence, okay? And it would make no sense for the matching correction to depend on that choice. So again, that's another way of saying what has to happen, which is that the final result had to be analytic as little m goes to 0, okay? I'm allowed to have these power corrections here, but I'm not allowed to have logs of little m, okay? So that's probably the most important conceptual point today, okay? And again, in my, suffering putting this together, that was the thing that wasn't happening for me. I knew that I needed the logs little m to cancel, and they weren't. And like I said, I guess I erased it now, but it's because I was missing that diagram with the heavy propagator in it, the tree level heavy propagator, which generated a factor of 3 log little m for me that I needed to make this cancellation happen, okay? Okay, so that's great. And so we can use this now, and the formulas that we wrote last time to run the couplings from the matching scale down to the low scale and see what happens. Okay? And again, the thing I want to show you is the way that, just like yesterday, right? I showed you that when we expanded the results from the RGE, we got back to the fixed order result, right? And so I want to show you that same reshuffling of things and recombination when we expand back. So we need the RGEs to do that, okay? So to run to the low scale, this is why I derived those general formulas for you 2 days ago, 3 days ago, who knows? Whenever it was, right? We derived the RGE in general in terms of Z factors for a theory with a C4 and a C6 coupling, right? So now the C4 we computed yesterday, the C6 running is here, okay? I have this anomalous dimension now. So I can just plug into those formulas from a few days ago, and that gives me the RGEs. So, so I was setting this up when I did that. So now let's use it. And so we have d log mu of C4 equals 3 over 32 pi squared, C4 squared plus 1 over 32 pi squared, m squared over capital M squared, C6. Okay? So I want to solve this differential equation respecting the rules of EFT. So in particular, because I have this power suppressed contribution, instead of just solving this thing and not thinking about the fact that I'm doing an expansion, I want to instead solve it iteratively in terms of power counting. okay? So that I'm always self-consistent about the EFT expansion. So in order to do that, and said another way, right? Power counting tells us C4 is a marginal operator, so I can have an infinite number of insertions of C4 without changing the power counting, right? That's the point of a marginal operator. And so that's what the RGE does, right? It's basically summing this infinite tower. But because this combination is power suppressed, if I'm only working in the EFT to one order in subleading power, it doesn't make sense to include all orders in this, right? Okay, so to do this expansion, we want to solve with power counting in mind. So we write C4 is C4 0 plus C4 1. Okay, that's the order in power counting. And then the differential equation dd log mu C4 0 plus C4 1 is 3 over 32 pi squared C4 0 squared plus 1 over 32 pi squared m squared over capital M squared C6. Okay? And so the 0th order differential equation, right? This is power suppressed. This is power suppressed. So the leading order thing is just what we did yesterday. So and the new ingredient is the power suppressed contribution. So notice that I dropped, when I did this, right, I dropped a cross term here, right? I should have put C40 plus C41, but then I dropped the higher power terms, right? So the differential equation for the second order contribution is just d log mu C42 is 1 over 32 pi squared m squared over capital M squared C6. Okay? And so putting this together, I get C4 resummed of mu low is C4 0 at mu match, or mu high, divided by 1 minus C4 0, 3 over 32 pi squared log mu squared over mu high squared, or let me just use match, mu match squared over mu low squared, plus C4 2 at mu high, mu match, plus 1 over 32 pi squared m squared over capital M squared C6 log mu low squared over mu match squared. Oh, 1. Yeah, 1. Thanks. Sorry. It's better. So it's technically, yeah. I was sloppy here. This should really, I think this is better to call this 2, because it's second order in lambda, right? Sorry. And then, good. Yeah, then these should be 2s. Good. Okay, so now we can put it here. We can compute the one loop amplitude at the low scale, where we use this running coupling. And then, again, the test that everything is self-consistent is we, like yesterday, we expand the resummed coupling out, and we should reproduce the full theory result. So one loop at the low scale does it make sense? Or yeah, please. No, let's. So the yeah, it's both subleading. So good. So it's the fact that it's subleading power and then also subleading in the coupling expansion. Sorry, I didn't say that completely right. Because so here everything is it's up to order lambda squared, but it's also up to one loop. Okay, so the claim is that that is a subleading higher loop correction. Yeah. Okay, so at the low scale, we compute the one loop corrections, and we just use the resummed couplings. So we get I amplitude EFT is minus I C4 at mu low, 1 minus 3 over 32 pi squared, C4 mu low, log mu low over m squared. So now we reproduce the log of little m squared contribution that can't, right? Before, we have that log little m squared in the full theory result, right? It canceled in the matching, which is not on the board anymore. But then it needs to be regenerated in the EFT, right? So the EFT here is giving us back the non-analytic structure of the low energy dynamics as we needed. Again, this is at threshold, so we don't see momentum dependence explicitly. And we also get IC6 over 32 pi squared, little m squared over big M squared, log mu low squared over m squared plus 1. Okay, so now I have let's see. Well, let me just write this. I think there's a typo on the board, unfortunately. So now I can put this all together, okay? And I have IA expanded EFT And this looks like the following. So I have I 1 over 10, 1 over 16 pi squared, C6, m squared over capital M squared times 3 log mu match squared over capital M squared plus 2 log mu match squared over mu mu match squared over, so I'm adding a 0 here to make a point. Okay, so this comes from matching. Then the RGE gives me minus I 1 over 32 pi squared, m squared over capital M squared, C6 log mu match squared over mu low squared. And the finite terms at the low scale give me minus I 1 over 32 pi squared, m squared over capital M squared, C6 log mu low over M squared. Okay. And this all combines into I C6 over 32 pi squared, 1 over 10, m squared over capital M squared, 3 log m squared over capital M squared plus 2 log m squared over mu match squared. Okay? So yeah, and that's the, yeah, so it's 0. It's mu match over mu match. So I'm adding this to make the point, right? You don't see, to see where each of these, how each of these combines to give you this contribution, okay? Yeah, and this I think is a typo. I'm sorry. Let's see what I have back here. Ah, I didn't write it correctly. Good. Ha. This is the problem with a calculation that's too complicated to do all the steps of. I have to trust my notes. I think this needs, yeah, this is the log m squared over mu squared. Okay, you'll have to go, to get the factors of 2, like I said, I was super careful in the lecture write-up. But conceptually, this allows me to make the following point, which is that, and here, by the way, I should also have said, okay, I only wrote the power suppressed part. Just again, because that's the thing I want to focus on. I want to focus on showing you what happens with this log little m big M. Okay, so yeah, correct. It's a 0. Yeah. So I'm adding 0 in order to, so that you can see the cancellation, right? Because this needs to cancel against this. Well, actually, yeah, there's non-trivial combination among the 3 lines. Okay, so so the point here, if you look at each of these terms independently, right, you see that what happened is we never encountered one of these logs with little m over big M. Okay, so this is what we mean when we say we separate scales. This is explicitly an example that does it. So the full theory result, which we must reproduce when we expand everything out and compute to fixed order, has this potentially large log in it, right? But the scale separation is taking this calculation and separating it into these three pieces. One from matching, one from running, one from computing loops in the EFT at the low scale. Okay? So when we draw these pictures, right? Mu match, mu low, right? Full EFT. This is the manifestation of what we mean by this picture. At the matching scale, if I take mu match to be of order m, no large logs, right? This log is 0, this is always 0, okay? The RG resums logs. So by definition, it handles large log problems, right? And it's a function of the two scales, right, that we run from the high scale to the low scale. So that's explicit here. And then at the low scale, I compute my loop involving the light fields. I get my non-analyticity in terms of the light parameters, okay? But it depends on the scale, on the low scale, because that's where I did the calculation. So this logarithm also can be kept small, okay? But it has to recombine into the original expression, okay, when you expand this middle step. So really all the hard work is being done here, right? Because the RGEs are connecting this completely perturbative result with no large logs to this perturbative result with no large logs. Okay. Yeah. Yeah, at tree level. But so the that means leading order in the power counting. Yeah, but yeah, exactly. That's leading order in the power counting. But in this calculation, so exactly. So this contribution in this toy theory is 0 because so this is the correct RG, but then you need to use the boundary condition, which is that the leading power contribution at this order is 0, and so that's why we have this boundary condition here, right? So this is the subleading power contribution. Yeah, yeah. Mm-hmm. Mm-hmm. Yeah, so that's right. I was implicitly solving the RGE for this example, right? So you're right. If I just was computing the RGE in the EFT without, my goal was to reproduce the behavior of the full theory, right? Which had this non-generic feature, right? I didn't include, for example, a tree level coupling. So if I had included a tree level coupling, it would have been much more complicated. I'm not sure I could have even done it analytically, right? So again, that was the So there's a lot of, in all these examples I did, right? By doing this non-generic full theory model, I often skirted some nasty technical problems. So that's a place where that's for sure happening. Yeah, yeah, yeah. I think so. No. Yeah. Wait. Let me see. Let me see. Um. Let's see. Yeah, that's true. There's the yeah, yeah. I'm sorry. Good, good. There's the tree level contribution. Exactly, exactly. There's the tree level contribution, and then the power suppressed contribution came at one loop. Um, no, no, that's to C6. That's to C6. Yeah, yeah. I'm sorry. I'm looking. Yeah, yeah. Good. You're right. You're right. I don't have it up here anymore. Um, but yeah, exactly. Um, Perfect. Thank you for correcting that. That's right. So maybe I can write it again. Um, the Yeah, C4 match, what I called C4 match, um, had both. So it had rho squared over 16 pi squared, and then um, no, because the two is counting powers, right? So this has both a leading power and a subleading power contribution. Yeah, yeah, thanks. That's right. So that's right. Exactly, exactly. Thank you. Exactly. And see, I get confused. It's very now because there's all these expansions going on, right? It's very easy to get confused. Here, right, I was just considering the power suppressed term because that's where this log was, and that's the thing I wanted to include. But of course, if you include all the terms, right, and hopefully you can it's plausible at least, right? You have to sit down and get the factors, but you get the whole thing, right? If you include the leading power stuff too. Um, yeah, exactly. Good. Anything else confusing, or that I said wrong? Okay. Um, so um, yeah, I think I should give you a break. I'm there's never enough time, but there's no point in. Let's take a break. Let's reconvene at 15 after, and then I'll show you how to think about this calculation in terms of the method of regions, and then we'll. Okay. So with the time we have left, uh, I want to I want to introduce a couple of other important concepts, and So this idea of scale separation is an extremely general phenomenon, and most of those EFTs that I was highlighting on day one have some version of this story built into them. Okay, so at some level, if you're looking to develop, or if you're looking for opportunities to apply EFT technology, okay, the one strategy is to look for problems with large logarithms, okay, and if you encounter situations where, especially where you have IR logarithms like this one, where there's a ratio of physical scales inside, this should, I really want to send home the message that this should scream out to you that there must be an EFT that could separate the scales inside this log and that you can use to then resum logs of this type, okay? So one strategy for, let's say you have an integral, like this heavy light integral, okay, and you want to know what is the EFT. There's this really kind of amazing technology called the method of regions, which allows you to systematically look for what the properties of the EFT should be. Okay, so so I just want to quickly show you how this works with this heavy light integral, and then I'll mention briefly another application and point you to my TOSI lectures for the details. And the key idea here is the method of regions is very closely tied to dimensional regularization. Okay, so it uses this fact that scaleless integrals vanish. And the way I think about it, I would argue, is that it really justifies everything we've been doing as far as using DimReg, which integrates over all possible momenta, right? In the context where we know that there are heavy particles that we're not including, right? So there's if you like, there's a puzzle, which we kind of talked about yesterday, which is when I have heavy particle decoupling and I'm working just in the low energy EFT where I don't have the heavy state, right? I compute the renormalization group evolution from divergences. Well, yesterday I argued that the RGE at low energies should not include the contribution from the heavy states. Nonetheless, DimReg is integrating up to infinity, right? And so there's a conceptual puzzle there, and it's explained by this method of regions. Okay, so let me work through the example, and then we can talk about it, make sure that the concept makes sense. So let's take this integral I. Okay, our new friend, the heavy light integral. So now we've seen that doing this integral gives you logs of little m over big M, okay? And we've seen that EFT in practice allows us to separate scales, right, and get logs with mu over little m and logs with mu over big M. So we can do this in a more systematic way, right? Here, we just took this example and we applied the tools, but I want to show you this method of regions, which allows you to sort of see this scale separation more generally. So here's the idea: is we have these loop momenta, and we are going to assume various power counting scalings of the loop momenta, inside the integrand before we integrate. We will Taylor expand consistent with those power counting assumptions, and then do the integral after we expand. Okay? So what do I mean? Well, I mean, in this case, it's kind of obvious. There's going to be two regions for this integral. Okay? One is going to be localized about big M. The other is going to be localized around little m. So I can make that manifest. I'm going to call one of them the hard region. So L hard goes like capital M, and then times. So this is just in order to do a Taylor expansion. So I'm assuming that it's homogeneous in all the directions because I don't want to break Lorentz invariance. Okay? And it's proportional to the scale capital M, because that's the fundamental scale in the problem. Okay, so the hard region is of order capital M, homogeneous in the momentum. When I assume this scaling and I apply it in that integral, the hard contribution looks like this. So I have integral d4L over L squared minus M squared L squared plus M squared integral d4L over L squared minus M squared L to the fourth, plus, of course, higher order terms. Okay? So you see what I did, right? I left the second propagator alone because L is of order M, or L squared is of order M squared. Is that better, right? But the first propagator, I'm now expanding in a power expansion. So the leading term is just sets little m to 0, and then I get this subleading term. Okay? So another thing you can notice here is that these higher power corrections have higher divergences. Okay? So my original integral was finite in the IR, but now I'm doing something funny here, okay? And I have to be careful about the way I think about the divergent structure. Okay? The other integral is localized about little m. We'll call that the soft region. So we're going to assume L soft goes like m, the fundamental scale, but now it's power suppressed. So it goes like lambda in all its components. Oh, yeah. Which part is this small? Okay. Yeah. So it's all good? Anybody else? Right? L squared's of order big M, so I leave this alone, right? L squared's bigger than this, so I Taylor expand this one, right? Okay. Now I'm going to do the opposite, okay? So I'm going to assume LS is now the order lambda, right? Order little m. So now this propagator I leave alone, right? Because these are of the same order, but this one is small. This is small compared to this. So I'm going to Taylor expand. Okay. And let's see. So now we can write I soft is equal to integral d4L over minus m squared, L squared minus little m squared. Again, plus higher order terms. Okay? So, and here I know where I'm going, so I'm only keeping the leading term here. I kept two terms there. Okay? You'll see why. So now I can just evaluate these integrals using dim-reg, okay? And I get I hard 0 mu to the 2 epsilon integral dl 1 over L squared minus M squared L squared. Okay, so I'm calling this, right? This is IH0. This one is IH2. And this evaluates to I over 16 pi squared, 1 over epsilon plus log mu squared over capital M squared plus 1. IH2 is, I'm not going to rewrite it. It's just this integral in d dimensions, put the mu to the 2 epsilon in front, and you get I over 16 pi squared M squared over capital M squared, 1 over epsilon plus log mu squared over M squared plus 1. And I soft, which is second order in power counting, comes out to minus I over 16 pi squared M squared over capital M squared, 1 over epsilon plus log mu squared over M squared plus 1. Okay? So if we put all of this together, we get I is I over 16 pi squared times 1 over epsilon plus log mu squared over capital M squared plus 1 plus M squared over capital M squared log mu squared over capital M squared minus log mu squared over little m squared. Okay, so this is exactly the result we got in the previous example, right? These mu's cancel and we get our log m squared over big M squared. We also had this divergent contribution, right? I had written it incorrectly at first, right, with the typo, but so this exactly reproduces the thing that we got in the full theory calculation that we then Taylor expanded, right? Yeah. That's right. Exactly. So the point, so you're exactly right. What you would really rigorously want to do, this is what people did before this was invented, is you would want there somehow to be a cutoff in this integration range, because indeed here you're neglecting the soft modes, so you would only want to integrate above some scale, say intermediate scale between little m and big M, and so you'd say, okay, we're going to split the original integral into a high region and a low region, okay? The magic is that the non-trivial claim here is then when I extend that, say for the hard one, when I extend that to 0, the thing I've added back is scaleless. And because I've done this expansion, indeed that's the case, is that the part that you're including the incorrect part that you're including contributes 0. That's why we can do this and use the dim-reg formulas that integrate over all momenta. Okay? It's crazy. It doesn't seem like it should be right. But again, this is this property of dim-reg that's so important for our EFT applications. Okay? And indeed, you can see that what this does, now if you want to identify, like we did in the EFT, you want to identify a mu high, right, what we called mu match in the previous example with this region, and a mu low with this region, right? I can just put my match here and low here. Okay, this should be match. This is what the EFT did for us, right? It separated the scales, and because we did the calculations at 2 different scales now, we got 2 different renormalization subtraction points, and so we could minimize all the logarithms. Okay? So the method of regions is really what underlies this way we use EFT, okay, this modern use of EFT. And I think I said this earlier, but this is what Georgi calls continuum EFT, okay? So a number of you have come in and wanted to understand a lot of the things we've been doing from the Wilsonian point of view, where you integrate out shells, which is the more intuitive picture for what EFT is really doing, okay? But the problem with the Wilsonian picture is that it's very cumbersome. And so actually doing calculations, even like the one we did here today, would be extremely difficult and painful. If instead you embrace the idea of continuum EFT, which is deeply tied to dimensional regularization, then you can use what you're really doing, okay, is you're relying on the method of regions. You're relying on the fact that scaleless integrals vanish. So yesterday when we computed the RGE for the low scale theory, for the EFT, knowing that there was another particle in the UV in our example, but ignoring it, that was basically this trick, okay? We were treating the UV as scaleless. We'd already sort of accounted for it in our local operator, so we expanded it away, and then it didn't contribute to any of the integrals, okay? Because we were using dim-reg. Okay, so this is the, yeah, please. So yeah, so in the in IH, it is technically regulating an IR divergence in IH2. Okay, so what happened? Notice, right? Thank you for that question, because this is the next point I wanted to make. Here, it's UV. Here, it's IR. Let me call it UV with an H. Here, it's UV EFT. Okay, just from the divergent structure, right? This is IR finite UV divergent. This is UV divergent IR finite, UV finite IR divergent. This is UV divergent IR finite. So the interpretation of these epsilons is indeed dim-reg here is regulating a UV divergence. Here it's regulating an IR divergence. Here it's regulating a UV divergence. But notice what happens when I combine all the terms to get that result. The thing out here, in the full theory, this is epsilon UV divergent hard, right? And what I've done is I have equated epsilon UVH with epsilon EFT, UV EFT. or soft. Sorry, I'm not being consistent there, right? This is the soft region, this is the hard region. So, my God, IR. Okay, so I'm equating this epsilon with this one because they cancel to reproduce that formula. Okay, so this is where we see that EFT converts IR divergences of the full theory into UV divergences of the EFT. And this is why we can use the renormalization group equations and that whole approach inside the EFT to resum logarithms. Because notice that this choice is exactly associated with this logarithm we spent over an hour trying to manage, right, in the example. Okay? So again, the method of regions justifies conceptually everything we've been doing all week. Okay? And in particular, it makes this completely manifest. We are assuming this when we're using continuum EFT because really we're relying on the method of regions. Okay. So I want to just quickly sketch another regions calculation, and then if you're interested in the details, I worked this out pretty. But yeah, please, before we move on, absolutely. No, please. Oh, so the H is corresponding to Taylor expanding that integral, assuming the loop momentum is localized in the hard region. Okay. What I get is at subleading order, right? This integral, when I go to the UV, it's finite, right? Because there's 4 powers of L here, 6 powers of L here. But when I go to the IR, I get a log divergence, right? Because this just becomes M, and I have L to the 4th over L to the 4th in the IR. So I took this IR finite integral, and I separated it into some pieces with IR divergences and some pieces with compensating UV divergences. Okay? This seems like a crazy thing to do. Why would you make your integral more divergent? Until you realize that this exactly maps onto what we do in EFT. Because the point is that by, we could do this heavy light integral in closed form, but often we can't, right? More complicated theories, higher loops, whatever, we can't actually do a closed form integration. All we maybe can do is a regions expansion, right? And that's when that's where the power of EFT kicks in, is because what we're doing is we're finding the separation into these different regions where the integrals simplify, because we went from a 2-scale problem with little m and big M both running inside the loop to a power series of single-scale problems. All of these in terms of a single-scale capital M, all of these in terms of a single-scale little m. Notice, right, the 1 over capital M is just factored out in the coefficient. All of the non-analytic structure, right, all the complicated loop stuff is going to always only involve little m in this Taylor expansion, okay? So it's by Taylor expanding the integrands, we trade complicated analytic structure for an infinite series of terms, right? But that's exactly what EFT does for us, right? We separate scales, so then we get some structure localized at a high scale, some structure localized at a low scale, but always single scale problems, so that we can do we can sort of do more integrals, harder integrals, okay? But it's exactly that when we do this procedure, we introduce these spurious IR divergences in the hard region that have to cancel the UV divergences in the soft region. We associate this with matching. We associate this with the EFT. And that allows us to use the RGE in the EFT, because RGE sums UV logarithms. It doesn't sum IR logarithms. Nonetheless, we can use it to sum IR logarithms in the UV because we've converted them into UV logarithms in the EFT. Okay. It's a deep idea. It's not a trivial thing. And in fact, I was, again, I keep bringing up Martin Beneke because he was visiting us last week. And, you know, I was just asking him, so he invented he's a co-author of the paper on this, Beneke and Smirnov from the 90s, somewhere in there. And I asked him, you know, there'd been a long history of people doing very hard integrals using EFT, all of this stuff. So I asked him, you know, why hadn't this been realized? What was the thing? What was the insight? And he said, you know, there was the great question, well, wait, shouldn't you be cutting these integrals off? And in fact, he said people like John Collins, who wrote that renormalization book, who's someone who really, really understands this stuff and has written a lot of very important papers on QCD, would be super careful about excluding that region, and that at some level Martin's insight was that all of those contributions were scaleless, and the hard work was convincing himself and his collaborator that was true, that this procedure would really hold. And you know, it's technically my understanding is that it's not it's sort of proven, but not super rigorously proven, but there's no known counterexamples. So this is believed to be true for Feynman integrals, and so anyway, it's but it justifies this continuum EFT approach. Okay. 15 minutes. Goodness. Yeah, I think maybe the last thing we'll do, and then we'll just call it a day, is let me sketch for you an even more interesting result, okay, that uses the method of regions. And then try to end a couple of minutes early because there's no gap between the lectures, so I don't want to. I want to give you a chance to breathe before you have to go through another 2-hour lecture. Okay, so there's famously, you can do the method of regions for so-called Sudakov integrals, which give double logs that are associated with IR divergences that you probably saw at least in passing for QED, for example, right? You have soft and collinear divergences in QED, and they manifest as double logarithms that appear at subleading order in the loop expansion, right? And there's this story, which is what we usually teach in QFT classes, that there are real emission diagrams which are IR divergent in the phase space integration. They combine with the IR divergences that appear in the loop expansion to give you something that's manifestly IR finite when you compute a physical observable like a cross section. Okay, so if that's not a familiar story to you, don't worry about it. It's not important for the point I want to make, but basically the intuition is that if you look, say, at the splitting function in QED, right, you just look at, which is really just a statement about this propagator. So if you take some source that gives you a fermion, you emit a photon, right? It's straightforward to just look at the kinematics configurations. When this photon's energy goes to 0, this propagator blows up. When this photon becomes collinear with the fermion, this propagator blows up, just from the kinematics, okay? And so it's those two kinematic configurations give us the so-called soft and collinear divergences of QED. And anyway, all this stuff is reviewed in my TOSI lectures if you're unfamiliar with it, but this is a you know, important and famous property of QED. So again, at this point, you know I love toy models, so we can write a toy theory for this double log in terms of scalars. So the following integral with so I have a heavy field, capital Phi, coupled to a light field this way. So now I have a cubic coupling between the heavy field and two of the light fields. I have cubic coupling, self-coupling of the light field, okay? This 3 propagator structure gives me the Sudakov double log. And so this just goes like integral d4L over 2 pi to the 4th, 1 over L squared, 1 over L plus P squared, 1 over L plus P bar squared. Of course, I'm being sloppy about I epsilon, right? But that needs to be there. These are massless, and so we're going to get an IR divergence from doing this integral, which in principle would cancel against diagrams with extra scalar emissions in this, if we're thinking about, for example, computing the decay of this heavy state. So this, I think, is the simplest example of a Sudakov double log, a soft and a collinear log, okay? We can regulate the IR divergence by adding a small mass, like, which is probably what you did in QED, or we can regulate it by taking these legs a little bit off shell. So that's what I'll do here, okay? So I'll have P squared and P bar squared non-zero, even though they're massless particles, okay? And the claim is that I can decompose this integral using the method of regions. So I'm not going to do all the details. I give very explicit formulas in my TOSI lectures, and then actually some of the integrals are quite a mess. So there's really nice lectures on SCT that I referenced there. I basically did one of the regions integrals in detail, and then for others, there's some nice appendix of some SCT notes by Thomas Becker and collaborators that if you're interested in the details. Anyway, in order to do this decomposition, really there's just one point I want to make, 2 points I want to make with this. So in order to do this decomposition, now it proves useful to specify the kinematics here. So these are light-like particles, so let's introduce some reference vector n, which just is a light-like vector, points in the z direction, a reference vector n bar, which is a light-like vector, points in the minus z direction. And when you do this, you can decompose any momentum along this light cone. Okay, this is called light cone coordinates. So basically, it's just a choice of basis, okay? You can convince yourself it's straightforward to derive this, just dot in various components, and you can see that this is self-consistent, okay? This perp means the components of momentum that are perpendicular to the n and n bar direction. So they point in these two directions, okay? And one of the key formulas is p squared is n dot p n bar dot p plus p perp squared. By the way, if you're getting into the details here, got to be careful whether or not this p perp is the 4-vector square or the 3-vector square. There's minus sign differences that, so anyway, I'm being quick here, but if you need to get the factors right, that's just something to note, okay? And then what we do in this business is we write p is n dot p n bar dot p perp. So we write 4 vectors in this 3 entry notation, okay? So then we can do the following method of regions decomposition of this integral, okay? So what we, so it turns out that not at all trivial, but turns out that the you can decompose this into the following regions. This is an H. So there's the hard region, the collinear region, the anticollinear region, and what's called the ultra soft region. Okay, and basically all you do is what we did in the heavy light example. You just take these denominators, you assume one of these scalings where the momentum P equals the heavy scale times n, and the momentum P bar equals the heavy scale times n bar. Okay, so these are, we're assuming that these, well, by momentum conservation, I think it technically needs to be this. If m is the mass of this heavy dude, then we're just doing a standard two-body decay, okay, where we have a massive heavy particle decaying into 2 massless ones back to back, right? That's exactly what this is. So you assume that scaling for the momentum, because that appears here. You assume these scalings for the loop momentum. This gives you 4 regions, okay? And the claim is that the total integral here decomposes into 4 regions, I hard plus I collinear plus I anticollinear plus I ultrasoft, and that you get minus I over 16 pi squared, 1 over m squared, log m squared over p squared, log m squared over p bar squared, plus pi cubed over pi squared over 3, plus order lambda squared, where lambda is this power counting parameter. This lambda is, say, p squared over m squared, p or p bar, okay? The virtuality. So, okay, I really need to wrap up. But you see you get this double log structure, okay? And one thing, okay, so I want to say a couple of things quickly. One is you could complain about all the examples that I've shown you so far that everything we did was trivial because we only were working with single logarithms, and single logarithms can obviously be factorized. If I have log little m over big M, I can obviously write that as log little m over mu plus log mu over big M, right? And so there's you know, probably, maybe it didn't occur to you yet, but you go home and you're thinking about these lectures, I hope, and you go, wait a minute, everything he showed me was totally trivial, okay? So I'm partly highlighting this example because if you, even if you don't work through the details, take 5 minutes, go look this up in my notes. It's a remarkable thing that this happens, okay? Now we have this structure of log squared, and it is completely non-trivial that it decomposes into regions. And you'll see all kinds of non-trivial cancellations happening, okay? You'll be very impressed. It's really quite remarkable. And in the notes, I do both this version and a version with a heavy particle here. Those are the 2 different Sudakov integrals, okay? So that's one thing. Another thing, which again, all the examples that I showed you may seem kind of trivial because the IR was obviously just little phi, but the method of regions reproduced that, right? The method of regions for our heavy light integral said there's a heavy scale and a light scale, okay? Now, this version of the method of regions is telling us there's a heavy scale, that's going to be matching, but now we have 1, 2, 3 degrees of freedom at low energies. And indeed, this approach, this is SCET, okay? And when you write the EFT for say, this model, then you need to decompose the full theory field into multiple modes, okay? So this is something that is a highly non-trivial fact of more complicated EFTs where I'm using some kinematic restriction, okay? I'm assuming that these things are almost light-like, and that's leading me to a different decomposition in the IR, okay? So we can use the method of regions. We can take an integral like this, where we get IR logarithms. We can use it to separate scales. So if you look at the contributions from each of these, you'll see, indeed, it separates the scales inside this logarithms, okay? And then we can use renormalization group evolution in terms of these EFT modes to resum those double logs and all of the subsequent subleading logs and so on, okay? And that's the program of SCET, but it's also just a general phenomenon, okay? And there's lots of examples of EFTs where the sort of underlying way to understand them is through the method of regions, okay? So I hope that I left you with a feeling that there is this, there's this deep principle underlying why effective field theory works, that it's extremely general, and that but that the methodology that we applied in these simple examples is at some level all you need to know, okay? If you find the right degrees of freedom, if you find the decomposition into regions, and then you just follow the rules of power counting and symmetries using these degrees of freedom, and you're careful, then you'll be infinitely powerful. You can do anything, okay? All right, this has been a blast. Thank you for amazing questions and all your attention. I hope to see you around. All right.